This video is the first of two parts related to Chapter 6.5, the last topic in this unit on chemical bonding, molecular geometry, and intermolecular attractive forces. And in this video, we're going to talk about molecular geometry. Molecular geometry refers to the three-dimensional structure of a molecule or polyatomic ion, basically what its shape is. And to quantify the molecular geometry, we need to specify all of the bond lengths in the molecule and all of the bond angles. However, we're more primarily interested in a qualitative description of the geometry that tells us what the shape is using a word or phrase. And to do that, we're going to use a theory called VSEPR theory that was developed in the early part of the 20th century. I like it because it's very intuitive, it makes sense, and it's extremely accurate. It really works well. And it's called valence shell electron pair repulsion theory, and the name pretty much describes how the theory works. The fundamental idea is that groups of electrons, including bonding groups of electrons and unshared electrons, in the valence shell of the central atom of the molecule or ion repel one another because they're made of negatively charged electrons, and they push the groups of valence electrons to be as far apart from each other as possible. And the geometry is determined by minimizing the repulsion between these groups of electrons around the central atom. To use VSEPR theory to predict the three-dimensional structure of a molecular ion, we're going to go through a series of steps, and here's the procedure. Step number one, draw the Lewis structure. You can't do anything until you know how many and what types of groups of electrons are around the central atom. You look at your Lewis structure and count the number of bonding groups of electrons and the number of unshared groups of electrons around the central atom. The bonding groups of electrons, or the bonded atoms, are represented with capital B. The unshared groups of electrons, or the lone pairs, are represented as capital E. Then we assign the molecule a molecular type using the nomenclature A, B sub X, E sub Y. What do those letters stand for? A stands for the central atom in the molecular ion. X stands for the number of atoms bonded to the central atom. Y stands for the number of lone pairs on the central atom. So once you've determined how many bonded atoms there are and how many lone pairs there are, you mentally arrange those groups in such a way as to minimize repulsion between the negatively charged electrons. And then once you've done that, you simply name the geometry and specify the bond angles. As you will see this year, we will only deal with 6 different molecular types, which have 5 different names. There are fewer names than types because 2 of the types are very similar and they share the same name. So now I'm going to systematically go through all the possibilities, give you examples, name the molecular geometry, and specify the bond angles. So let's begin with molecules in which there are only 2 groups of electrons around the central atom. That would be an AB2 type molecule, meaning 2 atoms bonded to the central atom and no lone pairs on the central atom. An example of that would be carbon dioxide. And if I draw a Lewis structure for carbon dioxide, you will see that there are 2 carbon-oxygen double bonds. How will those 2 bonding groups of electrons arrange themselves to stay as far apart from each other as possible? Well, clearly they will point in directly opposite directions from one another, making a bond angle of 180 degrees. That geometry is referred to as a linear geometry, and here is a picture that represents linear. So anytime you have a molecule in which there are 2 atoms bonded to the central atom, and that's all, they will stay 180 degrees apart from each other, and you will name it as a linear geometry. On the other hand, if there are 3 groups of valence electrons around the central atom and no lone pairs, I will classify that as an AB3 type molecule. An example of that would be boron trihydride, which has the formula BH3. If I draw a Lewis structure, I see it looks like that. Remember, boron is an exception to the octet rule. It does not need to have an octet. How will those 3 BH bonds arrange themselves to stay as far apart from each other as possible? Well, pretty much just as I've drawn them, they will point towards the corners of an equilateral triangle, okay? And they will form bond angles of 120 degrees, okay? Imagine that molecule being inscribed in a circle. A circle is 360 degrees. 360 divided by 3 is 120 degrees. We name this geometry trigonal planar. Trigonal because there are 3 bonded atoms. Planar because the molecule is completely flat. In order to stay as far apart from each other as possible, those 3 boron-hydrogen bonds will remain in a plane pointing towards the corners of a triangle, and here is a picture of trigonal planar geometry. Another example of a molecule with three groups of valence electrons around it would be an AB2E type molecule. This is a molecule in which there are two atoms bonded to the central atom and one lone pair on the central atom, as represented by the letter E. An example of this would be sulfur dioxide. Here is a Lewis structure for sulfur dioxide, and although you do not need to draw the Lewis structure to represent the molecular geometry I did in this case, you can see that the three groups of electrons, which consist of an SO double bond, an SO single bond in this resonance structure, and a lone pair, still point to the corners of an equilateral triangle, giving me a bond angle of 120 degrees. Now, I can't call this trigonal planar because there are only two bonds, not three, but simply looking at the geometry, a good way to describe it is bent. Some books say angular, some books say V-shaped. Either one is fine. I call it bent. Now, it gets a bit more complicated when we have four groups of valence electrons around the central atom. An AB4 type molecule would be one in which the central atom has four atoms bonded to it and no lone pairs. An example of that would be methane, CH4. If I draw a Lewis structure for methane, I see that I have four carbon-hydrogen single bonds and no lone pairs. You might initially think that that would be a flat, square-shaped molecule, but in fact, keeping it flat would not get the electron groups as far apart from each other as possible. This molecule has to go three-dimensional, and it does so in the following way. Okay? As I've drawn on the left, of the four carbon-hydrogen bonds, two of them are in the plane of the board. Those are the ones pointing up and to the left. One of them is sticking out towards you. Putting it at the end of the wedge line means that it's pointing out of the plane of the board towards you. The other one is going back away from you. Okay? You don't need to draw it like that. I'm simply drawing it that way in order to try to help you visualize what the three-dimensional structure looks like. Okay? Now, what this actually looks very much like is a tetrahedron. The object on the right is a tetrahedron. It is a solid object made of four equilateral triangle faces. And what you notice is that if the carbon were at the center of the tetrahedron, each of the four hydrogen atoms would be at one of the vertices. Okay? And therefore, this geometry is called a tetrahedral geometry. So anytime you have four atoms bonded to the central atom and no lone pairs, we say that this is tetrahedral geometry. The only random non-intuitive piece of information I want you to know is that the carbon-hydrogen bond angle is 109.5 degrees. Okay? Did I indicate the bond angle in the previous case? I did. Good. Okay. Now, let's look at two other examples of molecules in which there are four groups of electrons around the central atom. If there are three bonded atoms and one lone pair, and therefore the molecule is an AB3E type molecule, an example of that would be ammonia. If I draw a Lewis structure, I see that these four groups of valence electrons are still pointing towards the corners of a tetrahedron. Now, however, only three of them are bonds and one is a lone pair. Okay? So the word I'm going to use to describe this geometry, again, because there are three bonded atoms, I'm going to use the word trigonal, but I can't call it trigonal planar anymore because that lone pair pushes the bonds out of planarity. It looks like a pyramid, so I'm going to call this trigonal pyramidal geometry. Okay? And trigonal pyramidal geometry looks like this. There are my three nitrogen-hydrogen bonds forming the sides of a pyramid, and not shown in the diagram is a lone pair. My final example of a molecule with four groups of valence electrons would be one that falls into the AB2E2 type category, okay, meaning that there are two atoms bonded to the central atom and now two lone pairs on the central atom. An example of that would be water, H2O. If I draw a Lewis structure, I see that I've got two bonded atoms and two lone pairs. Well, once again, as in the two previous examples, the four groups of electrons point towards the corners of a tetrahedron, but now because only two of them are bonds, I'm going to call this also a bent geometry. Okay? And there's a diagram. Because both the bent geometry and the trigonal pyramidal geometries come from a tetrahedral arrangement of electron groups around the central atom, they also have bond angles of 109.5 degrees. Okay? Now, to help us understand this a little bit better, let's consider the molecular geometry of ammonia, as I showed a couple of slides ago, an AB3E type molecule. on the left I see a diagram that has the nitrogen in the center of a regular tetrahedron and the 4 electron groups pointing towards the vertices. On the right you see that 3 of those electron groups correspond to nitrogen-hydrogen bonds. The 4th pointing up is a lone pair, and again the name of this geometry is trigonal pyramidal. Here is a depiction of the molecular geometry of water, an Ab2E2 type molecule. Again, on the left we see an oxygen atom in the center of a regular tetrahedron with the 4 electron groups pointing towards the vertices. Now, on the right you see that 2 of those electron groups are bonding pairs of electrons and the other 2 are lone pairs. That gives me my bent geometry. Okay? Now, so let's summarize. Here are our molecular geometry types. If I have 2 electron groups around the central atom, an Ab2 type molecule, the geometry is linear and the bond angle is 180 degrees. If I have 3 electron groups around the central atom, there are 2 possibilities. Ab3 trigonal planar with 120 degree angles, Ab2E bent, also 120 degree angles. For 4 electron groups, there are 3 possibilities. Ab4 tetrahedral, 109.5 degrees, Ab3E trigonal pyramidal, 109.5 degrees, and also Ab2E2 bent, 109.5 degrees. Okay. Now, let's take this a little bit further and consider molecules with what are called expanded valence shells. It turns out, as I believe I mentioned in a previous video, that if the central atom is in the 3rd period or lower, its valence shell can actually accommodate more than 8 electrons. Now, you're only going to see this in this class briefly. I'm not going to hold you accountable for it on any assessments, but for those of you who will take an additional chemistry course, I want you to be aware of the fact that these expanded octet molecules do exist. An AB5 molecule would be an example of a molecule in which there are 5 atoms bonded to the central atom and no lone pairs. Well, if there are 5 atoms bonded, that's got to be more than an octet of electrons. An example of this would be the molecule phosphorus pentafluoride. And it turns out in phosphorus pentafluoride, here's how the 5 PF bonds are arranged. 3 of them are in a trigonal plane with bond angles of 120 degrees. The remaining 2 are in a linear orientation perpendicular to that trigonal plane, such that the angles between the trigonal plane and the linear orientation are 90 degrees. This geometry is referred to as trigonal bipyramidal because it looks as though you have 2 trigonal pyramids, one on top and one on the bottom. And here is a depiction of the trigonal bipyramidal geometry. The 3 groups in the trigonal plane are referred to as being in equatorial positions. And the 2 in the linear orientation perpendicular to that plane are referred to as being in the axial positions. The final example of a molecule with an expanded valence shell would be an AB6 type molecule in which there are 6 bonded atoms around the central atom. An example would be sulfur hexafluoride. Well, this forms an especially symmetrical molecule in which there are 6 sulfur-fluorine bonds, and every single one of them is exactly 90 degrees apart from the other. In our AB4 molecule, we said that the arrangement of the bonded atoms pointed towards the corners of a tetrahedron. Well, in this particular case, the fluorine atoms would be at the corners of a solid object that has 8 faces, each of which is an equilateral triangle. That object is called an octahedron. Therefore, this geometry is called octahedral geometry. And it looks something like this. Okay? But once again, for these final 2 examples, you're not accountable for those. I simply want you to know they exist. Now, what if the molecule has more than one central atom? Okay? All the examples I looked at so far, there was just a single atom in the middle with 2, 3, or 4 atoms bonded to it. Well, let's take an example. If I give you the formula H2N, CH2, CH, CH2, we can't give one word to describe the geometry of the entire molecule, but what we can do is name the geometry at each atom. Well, before we do that, we're going to have to draw a Lewis structure. I have typed the elements in the order in which they're attached to each other. So H2N means I have 2 hydrogens attached to a nitrogen. CH2 means there is a carbon attached to that nitrogen with 2 hydrogens attached to it. CH means there is a carbon attached to that last carbon with a hydrogen on it. CH2 means there is a carbon with 2 hydrogens on it. Okay? Now, if I count my valence electrons, Clearly, we haven't shown all the valence electrons because not everyone has their octet satisfied. I'll simplify the formula as C3H7N. 3 times 4 plus 7 times 1 plus 5 equals a total of 24 valence electrons. I've drawn 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 by putting in single bonds. That means I have 4 more valence electrons to distribute in order to satisfy octets. Clearly, the only way I can satisfy nitrogen's octet is to put a lone pair on it. The only way I can satisfy the octets of the 2 carbons on the right-hand side of the molecule with only 2 electrons is to draw a carbon-carbon double bond. So now we are going to look at the nitrogen in each of the 3 carbons, classify it using the ABE system, and then name the geometry. So the nitrogen has 3 atoms bonded to it and 1 lone pair. That falls into the AB3E category. Therefore, the nitrogen has a trigonal pyramidal geometry. The first carbon falls into the AB4 category because it has 4 atoms bonded to it, 2 hydrogens, a carbon, and a nitrogen. Therefore, we would say that that carbon center is tetrahedral. Each of the 2 remaining carbons is bonded to 3 other atoms, a carbon and 2 hydrogens, or in this first case, 2 carbons and a hydrogen. Each of these then is of the AB3 type, so we would say that those carbons are trigonal planar. Okay? So simply by zeroing in on a particular atom, you can see how many atoms are bonded to it, how many lone pairs, and you can name the geometry at that atom. In the next video, we will talk about how the molecular geometry influences important properties like the polarity of the molecule and how the polarity of the molecule influences what are called intermolecular attractive forces. We'll see you then.